Okay, thanks for coming. This is a joint work with my collaborators, Harens, Irshowitz, and Ambroise Lafont. Um, let me give a quick idea of this talk. What is an abstract programming language, and in particular, an untyped functional abstract programming language? I would say that there are a few things that that are essential to specify a programming language, which are syntax for programs, which we call terms, and a well-behaved substitution, which respect the syntax, and a syntax for reductions to specify the computational steps, and the models, which are essential for doing semantics. So our work is a framework, a theoretical framework for specifying a programming language with all those aspects. And if you want to keep a simple example in mind, you can think about lambda calculus with beta reduction. And I will discuss a little bit an example at the end. So let's start with the ingredients of our work. There are basically two main technical ingredients. One is initial semantics. I know that most of you know what initial semantics is, but let me fix some ideas and terminology. So I would say that there are three basic steps for initial semantics. The first step is to establish a signature, which is an abstract description of your language. And the second step is to give a notion of category of models. So models are where your program takes the semantic. And finally, you need a theorem. You need a theorem that proves that this category of models has an initial object. The initial object is your programming language in some sense. And so if you have done all this, the initial object is the language, and the initial morphism are the semantics of the language. If you are lost, let me quickly give these toy examples of natural numbers. So you have the classical syntax for natural numbers. And you have two constructors, which are zero and successor. So you can say that for this kind of languages, the signature is just a list of numbers, in this case, 0 and 1. Then you have models. So models here are sets with two constructions of arity 0 and 1. And they form a category, and natural numbers are precisely the initial object in this category. And the initial morphism gives you the classical recursion principle, okay? So this should convince you that indeed this is initial semantics is good to describe the syntax of a programming language. But how we said before, we need much more. We need substitution, we need equations maybe, or we need reduction, etc. So what we do is that we use initial semantics to do all these things, to express all those aspects of our computer language. And why we want to do that, or which is the advantage of doing that? The advantage is that you get, you generate semantic morphisms that respects all the feature of your language. So substitution, bindings, free and bound variables, and equations and reduction. So you can think the initial morphism as a certified compiler in some sense, in a very abstract way. And the second ingredient is monads and modules over monads. So why we need monads? For us, monads is just a way to abstract the notion of substitution. So it's an axiomatic presentation of substitution. And to give an example, let's consider the example of lambda terms, the monad of lambda terms. So we take we define this functor lambda, which is defined by the following rule. Lambda x is the set of lambda terms with free variables in x. So the easy example is when x is the empty set, you get the set of closed lambda terms. This is the easy thing. And then you have an embedding from x to lambda x, which is the constructor for variables, which gives you the unit of the monad. And you have the parallel capture avoiding substitution, which takes a map from x to lambda y and gives you a map from lambda x to lambda y. And the usual properties of substitution corresponds precisely to the axiom, to the laws of monads. So this is not enough. We have some notion of substitution that does not come from monad directly. And that's why we need modules over monad. So what is a module? A module over a monad R is an endofunctor endowed with an action of the monad R. So you have the endofunctor, and you have a kind of substitution, which we call M-bind. And the key point is that here you have the functor M, not the functor R. And of course, you have to give some compatibility conditions. And one easy observation is that every monad is a module over itself. That's easy. And of course, we have other examples of modules which are not monad. I will give you just two examples of modules. One is the product of modules. If you take two modules, the product is again a module. And the basic example is when you have a monad R, and you take R times R. Then it means that you have pairs of terms, and you can perform substitution in both terms. And this is a module over the monad R, but it's not a monad itself. And the second example is a little bit more tricky. Take a set underline n of cardinality n, and consider the functor x, the functor r power n from x to rx plus n. So this means that you have some a set of variables x, but you also add some other variables that you can think they are bound. And then you get a new kind of substitution that does not touch the bound variable. Okay? Again, this is a module, but it's not a monad. Okay, so with these two ingredients, we are able to specify a language. And I will give you two examples of things that we do with modules over monads. One is, so again, let's discuss the example of lambda terms. So application is a morphism of modules over the monad lambda. Indeed, it is a natural transformation from lambda x times lambda x to lambda x, which is natural in x, and that respects substitution. So it is a morphism of monads. And the other example is abstraction. And in this case, you have lambda 1x to lambda x. The derivation here, the 1, is needed because in the substitution you have a variable which is bound. Okay? Again, this is a module. This is a morphism of modules over the monad lambda. It's not a morphism of monads. And the second example is beta reduction. We can see beta reduction as a couple of module morphisms. So we have two module morphisms, one for the left-hand side and the other for the right-hand side. Everybody knows how beta reduction works. And here we remark that we have two parameters which are t and u. So we have two metavariables, t and u. And then we have a module of metavariables. The module of metavariables is lambda 1 times lambda. Why? Because you see that T is the argument of an abstraction. So you have to derive the module. And then you have two morphisms, which are what you guess. One source morphism that goes from lambda 1 times lambda to lambda and do the application of the abstraction, which corresponds to the left. And the other, which is the target morphism, which gives you the substitution of the two terms. Okay? What is our achievement more precisely? We have a stack of signature, and we started 2 years ago with a notion of signature for syntactic construction. So this is to specify monads with syntactic construction. So this is for the syntax of the programming language. Then we added a notion of signature for equations. This is a notion this is a notion that depends on the other one. So they are two layers that goes together. And when you do those together, you have a flexible way to specify monads. That's why we call it signature for monads. So this is a generic mechanism for building syntax for programming languages. And what we did now is to add the reduction rules to the framework. So now we have a notion of reduction signatures, which is able to specify not only the syntax of the programming language, but also the reduction rules. And OK, so what you can find in our paper. In our paper, you can find a notion of reduction monad, which is the mathematical abstraction of programming language. And also you can find a general notion of signature for reduction monad, which allows you to specify all the aspects of your language. So constructions, like application and abstraction, and equations, if you need equations, and also reductions to specify the steps of the computation. And finally, we give a category of models, and you can think models as the hardware where you can run your program, so the semantics of our programming language. And we have a theorem that gives, under suitable hypothesis, the existence of the initial element. So a theorem that says that the programming language actually exists with the given properties. And the second part of the paper is devoted to examples. So we have several kind of lambda calculi, which are presented using our framework. And so we recover the classical things. For instance, I would say that we have two main classes of examples. One class of example is about exotic rules and reduction strategies. And of course, we have the classical rules like beta eta reduction, head normal form, we had the normal form, and parallel beta, etc. And the second class of examples is about extensions of the lambda calculus. And we have two main examples. One is lambda calculus with a fixed point operator with the associated reduction rules, of course, and lambda calculus with explicit substitution. OK, thanks.
Do you have any questions from the audience?
Thank you. This is very exciting work.
Thank you.
In universal algebra, we have two different ways of doing categorical universal algebra, right? One is via monads. The other one is via Lever theories. And I can't help but look at this work and wonder if that analogy extends to the study of programming languages via this categorical model. Is there something like a Lever theory here?
I don't know. I think I should think about this. I'm not sure about what to say.
All right, thank you very much.
We have a question from Slider. The question is, what would a reduction monad transformer be, assuming that this notion makes any sense?
I didn't mention it, but the signature form a category. So perhaps, this is just an hypothesis, we can think about a functor from signatures to other signatures. So for instance, an endofunctor of the category of signatures. And that would be probably something that transforms a language in another language. I have to think if this can work, but it can be a nice thing to think.
So you said that you have a theorem ensuring the existence of a model and under some hypothesis, and I assume lambda calculus
Yes.
verifies this hypothesis. So what's the model that you obtain in this case?
The model?
Yes. Is it like a known model? Is it a new kind of model?
Well, what you get is something which is precisely isomorphic to the object that we already know. So the example I mentioned are examples that are already known, and what we get is a category where the already known calculus it's the initial element. So for instance, if you take a signature for lambda calculus with a fixed point operator, you get as initial element precisely the lambda calculus with the fixed point operator that everybody knows. But the point is that you can use it to experiment and to build possibly more creative calculi.
Can modules be given in a modular way? That is, can I build up the understanding of a language piece by piece?
Yes, this is yes, thanks. It is a very good question. So there is a property of modularity, which means that if you specify, you have a kind of push-out property in the category of signature, and the models are well behaved with respect to this. So you can compose programming languages.
We have time for a few more questions.
Hi, thank you for your presentation. It was really cool. You mentioned in your paper that you want to extend this to the simply typed lambda calculus. Could you provide an outline of how types would fit into the bigger picture here?
The simply typed you mentioned, yeah. So basically this is about changing the base category. Here the basic category is the category of sets. And to do something more complicated, you have to change this and probably take the category of families or things like that. In principle, should be doable, and there are also some previous results in this way. So could be one of the next steps.
Do we have any more questions from the audience? Well, in that case, let's thank our speaker again.
Thank you.